In the last lesson, we explored the relation between negative exponents and inverse numbers. Essentially, we found that any number raised to a negative number is in fact the inverse of the same number without the negative exponent. For example, we found that 2 to the negative 2 is the inverse of 2 squared. As we were working our way through some of the examples which are thought of for us, we found the final example having a product of a rational number and a whole number, both raised to a negative power. This combination of exponents created a rational expression. Just to recall, the question was 1 over 5 to the negative 2 times 5 to the negative 1. If you remember your rules for multiplying a number into a fraction or a rational number, you would recall that you can multiply your whole number into the denominator of the rational expression. So 1 over 5 to the negative 2 times 5 to the negative 1 would become 1 times 5 to the negative 1 divided by 5 to the negative 2, which simplifies to 5 to the negative 1 divided by 5 to the negative 2. Here we have a new type of expression we haven't seen before, a rational number with an exponent in both the numerator and the denominator. There are many times when we find rational numbers with exponents in both parts of the expression, so it's important that we learn how to deal with them, which isn't hard at all. In fact, it's quite similar to the product rule. The expression 5 to the negative 1 divided by 5 to the negative 2 isn't a good example to actually learn the quotient rule, because we could just simplify the terms and get 5 squared divided by 5. For now, we're going to use variables. Recall that when we learned the product rule, we simply added the exponents together whenever like bases were being multiplied together. For example, x cubed times x squared equals x times x times x times x times x. We learned the rule by spelling out the variables and adding them together. We will do the same with the quotient rule. Let's say we have x to the fifth power divided by x to the third power. Just like with the product rule, we're going to spell out the expression as x times x times x times x times x divided by x times x times x. Remember in the last lesson, we encountered a situation where we divided a number by itself to equal 1. We reuse that property of division here as well. We have 5 x's on top and we have 3 x's on the bottom. Therefore, we will only divide 3 of the top x's so that we can clear the denominator. So we'll cross out 3 of the x's and we are left with x times x. Going back to the algebraic expression, x to the fifth power divided by x cubed, we will see that it is equal to x squared. Using the same format with the product rule, we have arrived at a definition for the quotient rule. For all real numbers a and all integers m and n, a to the m power divided by a to the n power equals a to the m minus n, for a not equal to 0. This states that for all non-zero real numbers a and all integers m and n, if we have a rational expression with the exponents and the numerator and denominator with like basis, we can subtract the exponent and the denominator from the exponent and the numerator. We call for non-zero real numbers for 2 reasons. We cannot divide by 0, and 0 divided by any number equals 0. Let's work a few examples. Number 1, 7 to the 7th power divided by 7 to the 5th power. Here we show the simplicity of the rule. The basis in the rational expression are the same, so we can subtract the exponent of the denominator from the exponent in the numerator. This gives us 7 to the 7 minus 5 power, which equals 7 squared, which equals 49. Number 2, 3 cubed divided by 3 to the 6th power. In this example, we have a rational expression with a larger exponent in the denominator. Since the bases are the same, we can see that our number will have a negative exponent. We have 3 to the 3 minus 6 power, which equals 3 to the negative 3. We now utilize the negative rule for exponents and take the inverse, giving us 1 over 3 cubed, which equals 1 over 27. Number 3, 2 divided by 2 to the negative 3 power. A number always has an exponent. If none is written, we understand it to be a power of 1, which represents the identity property of multiplication. So we can still utilize the quotient rule here. We have 2 to the 1 minus negative 3 power, which equals 2 to the 1 plus 3 power. Remember that when you minus a negative, you are left with a positive. So this becomes 2 to the 4th power, which is 16. Number 4, xy squared divided by y cubed. Now we have multiple variables in our expression, x and y. Our x does not have anything we can do with it, but we have multiples of y in the denominator and denominator. Using the quotient rule, we have xy to the 2 minus 3. We don't need parentheses because our exponent isn't affecting the x. This leaves us with xy to the negative 1 power, which simplifies to x divided by y. Number 5, x to the 2y power divided by x to the 5y power. Here we have a quotient with like basis, but also variables in the exponent. We don't have to worry about how to deal with the variables in the exponent here. We treat them the same with their coefficients. Using the quotient rule, we have x to the 2y minus 5y power, which becomes x to the negative 3y. We use the negative rule here, giving us 1 over x to the 3y. If that still confused you, we could use the distribution property instead to help understand that we are not doing anything with the variables in the exponent. At our second step, we had x to the 2y minus 5y. Recall the distribution step. We can factor out a common multiple to simplify an expression. That works inside of exponents too. Look at the expression in our exponent. We have 2y minus 5y, with a common multiple factor being y. So if we factor out this y, we have y times 2 minus 5. Looking at our whole expression now, we have x to the y times 2 minus 5, which becomes x to the y times negative 3. It's customary to have the exponent in front of the variable. So we rewrite it as x to the negative 3 times y, which simplifies to 1 divided by x to the 3y. We have arrived at the same answer. Number 6, x to the 5th power times y to the 4th power divided by x to the negative 2 times y. We have multiple variables, each having their own exponents here. We simply take this one step at a time and rewrite the entire expression as a single term. This becomes x to the 5 minus negative 2 times y to the 4 minus 1. We simplify to x to the 5 plus 2 times y to the 4 minus 1. We now evaluate the exponents to x to the 7th power y cubed.